Oké, cool.
Wacht, hè.
Ik ben terug en het werkt nu.
Dag Lien, hoor je mij?
Hoor je mij ook?
Yes.
Super.
Okay.
Sorry, er was nog iets mis met mijn privacy settings.
Oké. We zijn ondertussen normaal gezien aan het streamen naar YouTube. Hè? Ik geef het even mee.
Alles wat we nu zeggen staat forever op YouTube.
Yes. En Istvan geeft ook al commentaar dat de stream is gestart. Dus dat is goed.
Alright.
Oké, dus het lijkt te werken. Dat is goed.
Hebben we ergens de YouTube-link?
Ja. In de invite van de meetup.
Ik heb die ook wel ergens.
Ja, het is gewoon gemakkelijk.
Ik zal die even...
Ja.
Ik zit nu in de chat normaal gezien.
Ah, super. Dankjewel. Ja. Dus als wij backstage gaan, dan hoorde jij ons nog, Chris?
Geen idee of ik jullie dan nog hoor, maar ik ga eigenlijk niemand backstage sturen, tenzij jij dat zelf wilt. Gewoon iedereen fijn in die groep laten.
Dus ik moet er altijd presentabel uitzien. Shit.
You can just walk away from the screen, right? And then you're just broadcasting your cell. What was it? What is it? The attic. Jesus.
Hela complimenten.
Hallo.
Hey, Benjamin, welcome. I'll speak English because we're already live and not everybody speaks Dutch.
Yep, good idea.
Great.
Well, we planned this 30-minute head start to get everything right, but since I think, Victor, it was you who recommended us to use StreamYard, we only need like 3 minutes, so yeah. So what we're going to do the rest of the 27 minutes, I have no clue.
Tell jokes, sing a song.
Ooh, if I start singing, definitely our audience will drop. So.
But I have plenty enough time to rejoin. So
that is true. So welcome everybody. Glad that you can all make it. This another lockdown edition of the Data Science Leuven meetup. I'm again the technical person, but Lien will be hosting and presenting. All right, cool. Yeah, let's wait until it's 19:30. There's not much.
Should I try sharing my screen once more?
Yeah, go for it.
Okay. Wait a second.
Maybe let me try that too.
Okay.
Yeah, Jeroen. Bam, this is your screen, Jeroen. So okay. Now from habit to digit is being broadcasted. So
all right.
Turn it off again. Yeah.
Cool.
Somebody else wants to share their screen? I'll try.
I'll stop sharing mine. I don't know if it's necessary.
No, you can just keep it open. That's easier for Chris. I
think. Then I will.
Depends on what you're planning to open on your screen.
You should be aware.
Yeah, that's true. I share the tab of my browser. That's generally a good idea. Just the tab.
Yeah, Victor, I also see your screen now of ML6. Yes, it's there.
Perfect.
Mm-hmm.
How about this?
Yeah. All right. Benjamin, yeah, now this is yours, natural language processing with I know. Yeah, it's also being broadcast.
Great, thanks.
Awesome. Yeah, Lien, I'll project your screen again then, because that's the night's slide. Am I the only one whose screen is flickering? My screen flickers a bit, but I'm afraid if I reboot my browser that this is being disconnected or something.
Mine is not flickering.
Okay, then I'll just...
No, everything seems fine.
Okay. Yeah, then I'll just leave it here. And Peter van den Abele, first online meetup, welcome. And Bart also joined, and Enrique. Cool. I'm getting a compliment from Bart. Awesome. I'm gonna grab some drinks while we wait, right?
Same here.
Around.
Good idea. I'm gonna do the same. There we go. Cheers.
Cheers.
Cheers. Lien,
I will do that.
yeah. You get lightning tips from Bart. Hey, Bart, when will you ever present at the meetup? You've been there a few times, and we're still waiting for your proposal for a talk.
Is this better? Nah, it's a bit dark.
It's very dark.
Yeah, the light is a bit blinding.
Live editing my home office setup. Things I thought I'd never do on YouTube.
Yeah.
There we go. This is better, no?
Yes.
Yeah. Now you have a light in front of you.
Nice. I should have bought me one of those circle lights. What do you call them? Like those?
A ring light.
A ring light.
Yeah.
Chris is up to date with the cool kids.
I don't have a ring light though.
But at least you know the name.
Yeah, that is true.
True.
I'm enjoying my last days of freedom. So for those who are in the stream who don't know, about to become a dad for the second time. I won't sleep anymore for
Congratulations.
weeks. Yeah.
Congrats.
Now I know what's coming, so no need to congratulate me. Sleepless nights. No, we're looking forward to it.
There we go.
When is the delivery date that you date?
Well, on Monday, actually. All before, but the latest Monday we have to go to the hospital. Sunday evening already, and then Monday should be D-Day.
All right. Exciting. So today was already for you probably a bit under tension because, you're never sure in these last couple of days before the date.
Actually, I can get a text from my wife.
Don't make it worse.
Yeah, if we see you disappear.
The peak drop.
Indeed. Then I have more important things to do.
And we have more important things to cheer to.
Exactly.
Indeed. Hey Bart, I see you want to present at a non-virtual event. Well, are you discriminating now? What's wrong with a virtual event? It's not good enough for you?
And now it's going to take 2 minutes for Bart to respond because it's we have a delay on the meetup.
Yeah.
Nice.
He might have just proven his point.
Perhaps.
Yeah, maybe. So is this the first time presenting, I guess we should call it a webinar for you guys, or do we have any webinar pros here?
I've done this before, and it's the stream yard was the best one so far in terms of technicality. So that's why I recommended it. So it works quite well.
I think it's kind of funny that whatever I say is going to be on YouTube forever. I love you, Mom.
Okay, Lynn was late with the Mother Day present. That's clear.
But what is weird, I think the presenters will see it, is that the moment you present, you're basically looking just at your screen, so you see no human feedback whatsoever. It's weird. It's new.
Yeah. You don't know how the audience is responding to what you're saying. My jokes are usually really bad, but now they could be even worse.
It's like presenting to a really polite audience.
Yeah, true. That's true. Yeah.
No, but it is true. When I'm talking myself, I also try to get a feel of the audience, and like measure the response in the room. That's not possible now, so it's a bit more difficult. Yeah.
We'll see.
Bart doesn't look good on the camera. Bart, I want to say something about that, but since it's being recorded, I won't. Hi, Herman. Welcome.
Welcome.
Hello, Herman.
Ooh, we
No
have
other.
a coder. Who would it be?
Bycoder. Yeah.
Have any of you guys ever open sourced anything before? I know Chris has, but
Yeah. Nothing fantastic, but yes.
so do
Well,
you,
it's actually,
sorry, go ahead.
it's the subject of what of my my little session. So
Oh, wow. Cool.
it is a first for our company. That's right.
Nice.
Yeah.
I'm thinking about open sourcing something, but it's more difficult than I thought.
Well,
It depends on how big your legal department is. The bigger the legal department is, the harder it gets.
We have no legal department, but I just mean in terms of documentation and stuff. Like,
What?
yeah. It's exactly where you put the bar. Eh? Like if you just do a git push and you're done, and then you attach an Apache license, then it's open source, right?
Works on my computer.
Indeed, ship it.
yeah.
If you ever see a demo with local hosts, don't trust it.
The problems usually only start when people start using it, right? That's when, in the beginning, I've heard a lot of people comment that way. Like in the beginning, it's super exciting, and then people are using it, and then all of a sudden you get these crazy requests, and then it's like, oh shit, they're really using it, and then yeah. I know our team lead, Joss, he has the Pandas profiling library, which he created, and that really took off. And yeah, at some point he was really looking for people to take over the maintenance because yeah, it was a lot of work to as new updates kept coming out to keep everything running. So yeah, it's not something to be underestimated.
Yeah, I also hear, what's the guy Wes, the guy who created Pandas, Wes something?
Wes McKinney.
Yeah. He also sometimes complains about that once you have put something in open source, like people just treat you as a resource. Like, please add this feature. Let me know when it's done. Thank you.
Exactly.
Free labor. I mean, who can blame them?
Yeah.
Yeah, but it's the attitude, right? It's
It's true. I always say please and thank you whenever I report a bug. But I do report a lot of bugs on open source projects.
Yeah. So Maxi Drones asks the question if the stream is in English or Dutch. The stream will be in English. I think everybody here speaks Dutch, well, from the speakers, but the audience is a bit mixed, so it will be English talk.
Oh, by the way, Chris, it might be worth it to have a little banner at the bottom that tells people to scroll to the live feed, because I know Sophie had issues last meetup. Yeah, there, but then just tell them to scroll to the latest, because she was half an hour behind. She refreshed her browser and then she lost two speakers in between. So that was kind of lame.
Rough.
Yeah.
You can also click on live in YouTube. If you click the word live, it also snaps back to.
Ah, perfect. See, that's a good banner. Click the word live. We have a streaming pro.
Yeah, but now we lose one face basically. Yeah, Victor is gone. Do we want Victor or do we want the banner?
You can put me down there. Can't you move me? No?
No. I can do this though, but then your screen is gone.
But that's okay. I think people know it's gonna start at 7:30 by now.
Yeah.
I do heard that with GitHub contributions, it's a lot better, by the way, with the open source stuff. Like the pressure that's put on you, because usually it's the maintenance guys that then are very happy that people are contributing. Like if you send a pull request, and they're very nice on you. It's like, yeah, no one asked you to do this, so thanks for
Okay,
for
cool.
adding it.
It's
So
not always true though. If you
No, maybe I've had nice maintainers.
yeah, we at some point, well, no, I won't name the project, but we wanted to contribute back to a project, but maybe our code was just shit. That could also be the case. But anyway, when we tried to contribute, it was basically no, go away, no, that's stupid, no, okay.
Oof.
Yeah, I tried once too, and they made it so difficult. At first, they were like, "Yeah, we encourage everyone to join in and contribute back to the project." Then I tried, and it was just an endless stream of, "You did this wrong. This sucks. You should do this a different way." And then I just gave up. That's why I want to open source my own project. None of that.
Hey, but Lee, you want to open source? You want to open source something? What's it about?
I want to open source a research toolkit for recommenders that I've been working on. But it's very much a work in progress. But any tips or tricks would be very appreciated.
Well, you release it as version 0.1, and then you can break it all the time.
Yeah, that's the plan. 0.0.1. Like absolutely no stability. Do not expect any stability. We can change this overnight if we want to.
Yeah.
I mean, Scikitlearn is still version 0.22, I think.
No.
And
No.
Flux just released after like 8 years or something, version 1.
Oh, that's crazy.
True.
It is a proven open source strategy.
But like, if you look at games, it also regularly gets abused because they just say, "Oh, we're in alpha phase. Anything can change," but you still pay quite a large price to beta test it, so that they basically get income, but they can say, "Oh, but it's still in beta, so we don't really have to fix anything." Yeah, but I mean, let's be honest. You have games that are for 8 years on Steam in beta mode. So.
Oh wow, I didn't know that.
Yeah, but it's the same as with pandas.
Hmm.
Only you don't pay the price.
Hi, Kik. Joss is here. Hi, Joss.
Joss, we were talking about you.
Yeah.
Don't worry, it was nothing good.
Now I wonder which version Pandas profiling is. Did he release it as a stable version 1, or is it still in alpha?
Oh, I can look it up, huh?
He actually found people to maintain it, so it did get a recent update a few months ago, I think.
Is it version 2.8 already? 2.8.
2.8.
Oof, it's way past pandas.
Joss, we're all impressed. We're all impressed by your work on pandas profiling. I'll put a link in the chat.
And the README is clean. Very nice.
What is clean? Sorry.
The README. Sorry.
Oh, nice. Let me go and check it out now.
Yeah, Lien, so if you want to know how it's
I also
done,
have something to promote because our community member Sophie has just released an amazing video where she explains named entity linking. It's also on YouTube, so go check it out.
you should post a link then, otherwise people can't check it out.
I will. I'm waiting for Sophie to notice this, and then I will post the link.
Hey, the response is quite good. Sophie already sees this, so the delay is not as bad as last time. I think last broadcast we had like 2 minutes delay or something. This seems to be better.
Here we are.
I'm on a delay. Hey there, hi Maxime, welcome. I also see that Christophe Leroux has joined. He's an old colleague of mine at I-Know as well. So Benjamin, like all the old guys from I-Know are watching.
Yeah, terrific.
Yeah.
And Herman Roelens also knows us very well. I'm not sure if you still met him while you were at I-Know, but
I haven't met him. Yeah, and Derek also claimed he would join. So
I saw that.
yeah. Lina, where is the talk now of Sophie?
I posted the link, I think. No?
You
Oh, I did, yeah. It's not showing up on our feed, but it is on YouTube.
Hmm.
Weird.
Really weird, yeah.
I
Making
don't
sure
see
I
it
have-
either. I just see check it out.
Yeah, and the link is right above that. If you
No.
go on YouTube. No?
No.
That's all.
Oh, I
It
got
still
it
needs
here.
to be approved.
Maybe.
The
Yeah.
human workflow that somebody needs to check out whether it's not selling Viagra or anything.
Maybe, Chris, we need a banner that tells people to find named entity linking Spacey on YouTube.
I'll Google it. I'll be the Google for you. Named entity linking. Sophie probably then. If I enter, yeah, here. But it's 10 months ago.
No, that's for talk. But there's a recent video.
Yeah. Here it goes. Here it goes.
That's the one. Oh, we can just broadcast it. Fills up the last 8 minutes for us. Haha.
So Peter asks if I can see the Google accounts of all people watching, and Peter, the answer is no. I can just see anonymous statistics. I don't know if I can screenshot what I see, but I don't see who's watching. Let me see.
Oh, we have somebody from Portugal.
Nice.
Now is the moment that we should say, if you like our videos, please like and subscribe us now.
Oh my God. Yes, Chris, you keep doing that.
Yeah, I'm a social media manager.
Uh-huh.
Uh-huh.
I am terrible with social media, so.
Let's see.
I've always wanted to point at the bottom of the screen, though, and say something like and subscribe. Here? No, I don't.
You're pointing at Victor.
Yeah, sure.
You may be hearing some of that in the background. That's my kids watching YouTube.
And you don't? Wait, no, that's Chris.
No, it's
In the meantime, I'll do something useful and tweet the statistics I see while broadcasting.
Cool.
Statistics, I can't even type.
So how many viewers do we have?
At the moment,
45 actually.
yeah, exactly.
Wow, cool. All of that for us cracking
Someone
jokes.
just left.
Yeah, that's my fault with all of the like and subscribe stuff. By the time we get started, my beer is going to be finished.
Then you need another one.
But I can't just walk out, right?
No, you're the presenter.
How are we going to fix this?
Don't you have a butler in house that you can say, hey,
No,
bring me a beer, and then Sudo bring me a beer? No, that's okay.
Chris, I am streaming from my bedroom, which is also my home office. I spend like 23 hours a day in this place, so.
You have a boyfriend, right? So he should be able to bring you a beer, no?
I do, yes.
If you're watching now, he needs a beer.
Yeah, I don't think he's watching.
No. My wife neither. Like, she is actually in data science, and she's been telling me, yeah, I'll watch, so she never watches.
Yeah, no, he's not in data science, so I don't think this is going to be very interesting for him.
Right, 5 more minutes.
Cool.
You see, my call worked. Peter says that subscriptions are up significantly, so we have more subscribers now.
Yeah, they tripled.
Wow.
I'm like a growth hacker.
Yeah. I would change your official company title.
Company title. Yeah, my role in the company, growth hacker. No, I don't
Growth
like,
hacker.
I really don't like that. Well. Am I the only one intrigued by the F on Jeroen's shoulder? Yeah, Jeroen, what's the story?
And the
Yes.
F, it's faction. Huh?
I thought
No,
it
no,
was
it's
your
not.
last scorecard.
No, it's actually a present for my my girlfriend's best friend of hers had got a son, and it's called Flores, and it still has to be delivered, but in these times it's hard. So now it's just part of the room.
Cool.
But if you're
That's-
watching, there's your present.
Damn it! I spoiled it. Yeah, I'm not data scientist though, so very slim
Okay.
chance. But it's on YouTube forever, so
Yeah,
who knows?
true.
Yeah, by the way, you guys managed your hair quite well despite being in a lockdown. I'm not
Thanks,
keeping
Chris. I really try.
You just done.
No, all of you look really well kept, actually.
Presentable. All right.
Presentable, yes.
I even shaved that. Like,
Yeah, I did that
Yeah.
too.
God damn it.
After
You shaved the dry run. That was last week.
The dry run, I wasn't shaved for sure. I had a beard back then. I know because it takes 2 months for me to grow a beard, so I know what I'm doing.
Nice.
same thing.
Hey, I see Beth Cossé, of course. Sorry, I still don't know how to
Yep.
pronounce your name. He also joined. Hi, Beth.
Yep. Faction team member, just like Gaia.
Very nice.
Cool.
Very cool. But there's a bunch of people watching, I think, who haven't introduced themselves. So shout out to everyone who hasn't introduced themselves. Talk to us.
Exactly.
We want to know who you are.
Indeed. And give us feedback while the talks are going on.
Yes.
Yes, for sure. Tell us where you're watching from. I'm watching from Leuven.
Yeah. Yeah, Peter, we're also having a drink. Eh? I'm still presentable. Depends where you put the bar, right? It's like, when are you ready to open source something? It's like, when are you ready to stream to YouTube? It's like, oh, that's where the bar is, right?
Yeah. I think I'd place the bar quite high for both.
Hmm. Oh, yeah, almost.
You're getting some good recommendations there, Chris.
Yeah.
Bart, if you're brave, then you tweet a picture of yourself now, to also present yourself. Hey, Peter, welcome, first time.
Oh, cool.
Are you family of Bruno? Okay, Tessa also joined. Hi, Tessa. Robert from South Africa. Awesome.
Whoa.
Nice.
Cool.
That's awesome, huh?
It's really cool.
All right, I think we're about to start. Huh? So it's
Yeah.
like 1 more minute. We'll wait 1 more minute, and Lynn, I'll also already make your screen the presenter screen. No,
Perfect.
there we go. And I'll remove the banner thing, because if it's there the entire time, it's annoying. No.
Yeah, it's true. Now we can't see Victor anymore. That's a shame.
Yeah, there he is again.
Hey, Victor.
All right, Lynn. Good luck. It's
All right.
1:30.
My time to shine.
I'll mute the rest.
Again, a very big welcome from all of us, the organizers of Data Science Leuven, now Data Science YouTube. I won't take too much of your time, so let me start by, this is not weird. Okay, there we are. Presenting the schedule. We're going to start off with Jeroen Boei from Faction, who's going to talk us through a solution he built that will allow the elderly to stay at home for longer, which I think is very topical in the current times. Next up is Victor Song, who's at ML6, who's gonna show us something they built for video analysis on live streamed soccer matches. And we're gonna conclude with Benjamin, who's gonna present to us I know, which is gonna be open source soon, apparently. So I'm very curious to hear about all of that. Well, you all know we can't be together right now, but there's one plus side. That means that we can have beers throughout the presentations instead of just after. So join us all for a beer. One thing before we get started is I wanted to ask you guys if you had any more suggestions for how we could keep the community vibe flowing when we're not together, because it's difficult to keep a community going when you can't really see each other face to face or really talk to each other. We finally figured out the whole technical streaming thing with StreamYard. Thanks again, Victor. But now we really want to figure out how to keep the community alive. So if you have any suggestions, just place them in the comments on YouTube, or just contact us on Twitter, on Facebook, on Meetup, via email. SlideShare is a bit harder. You can't really talk to us face to face right now, but all of the others should suffice. And don't forget to also write down the date for the next Data Science Leuven meetup, which will take place on June 10th. Again, we'll start at 7 p.m. We'll be streaming live on YouTube. The link will be available up front. And since we're gonna have to be streaming for a little while, we decided to take the opportunity and invite an international speaker this time. So I hope you'll all join us then as well. So then, Chris, I think you can switch back to Jeroen's screen and we can get started.
All right. You have my screen, I assume?
Yeah, you're being broadcasted. Yep.
Okay, great. Okay, so my name is Jeroen. I'm a senior machine learning engineer at Faction, and indeed today I'll be talking about a solution that we built for Brussels-based startup called Jane, allowing elders to stay at home longer using technology. And so just a few slides about Faction. We build deep learning, machine learning, and artificial intelligence solutions, but we always focus on providing value for our customer, that over coming up with the most fancy algorithm. Because actually you'll see in today's project that I'll be presenting, the algorithms we use aren't all that fancy, but the transparency here, the clarity of the whole thing was really key. And so we decided to use really clear approaches. At Faction, we have a number of specializations. We have the biggest chunk of our machine learning team is actually specialized in natural language processing. We've also had a good spin-off called ChatLayer.ai, which is now a separate entity. And currently we're building a second product called MetaMaze, which is an automated document processing tool. But we're not all natural language processing specialists. I myself am from the sensor data and computer vision team. And today's talk, of course, is in this area. So I'll be going over the data science work that we did at Jane. And then in the end, I'll dive a bit deeper into Timescale, which is a technology that we used at Jane. And that's interesting to share, I think. So Jane allows people to stay at home longer, these elder people to stay at home longer, because it allows the people who are following up on them, typically their children, to keep track of how they're doing. Because typically people would call them every day, or they would pass by, but you can't be there all the time. And so after a while, you get worried that something may happen. And the topic of sending them to retirement home comes up. And of course, for these elder people, this is very disruptive. They want to postpone it as long as possible. And so this technology actually comes up with a compromise where people can stay at home longer in a safe way. And the children taking care will have peace of mind, knowing that everything is fine, using the mobile app that comes with this solution. So the hardware is shown here. The hub sends the data. They have some SOS buttons which are really clear, so I won't go into those about what they do specifically. But they also have motion sensors, and that's really the core of the analysis that we did. And these motion sensors they actually send out really simple blips of just true values whenever they detect changes in the infrared spectrum. They're passive infrared motion sensors. And you could have data like this. This is an artificial data set, but here we see 4 rooms, and throughout the day, we have these blips of motion happening in this room. And that's really the foundation that we have to work with for this analysis. We want to extract things like, okay, what time do they wake up? What time do they go to bed? But we also want to extract a more general pattern of expected activity to see if something weird's going on, like overall, in the overall situation is something weird going on. And that's actually quite tricky to do because these sensors, they detect motion, they detect changes in this infrared spectrum, but it's perfectly possible that a person enters a room and then sits down for a few minutes or even longer time without moving all too much. And they just become part of this infrared background, and the sensors will not trigger any motion at that point. And so it's really important for us to be aware that you can have situations where somebody's in a room for a long time without any sensor values, because if you would assume that because the sensor is not sending any data, there's effectively nobody in that room, we would maybe send a lot of alerts that motion has stopped in all rooms, and we'll get a lot of false positive alerts in the mobile application, and then people would start ignoring the app, and that's of course the last thing that you want. So fighting that is really a big challenge, making sure that we only send alerts when something's really wrong. And so the overall strategy we have to do that, to do that anomaly detection, is to build an expected activity pattern per room per time of the day, which we update daily. And then on the other hand, we will query the recent activity data, update that every 20 minutes. And then every 20 minutes, we will do a cross-check. So to see if the recent activity is still within the range of expected activity. And if that's not the case, then we'll send an alert, basically. Now that's very high level. Let's go a bit deeper. What you see here is just 3 example motion values that we would get from this type of sensor. And you may have noticed in the previous slide, I was talking about activity. I was no longer talking about motion. It's just semantics, but the way we thought about it was like motion is what's coming from the sensor. It's these 1 values on a specific second. It sends you a 1 value, whereas activity is for us more the continuous value, which is much easier to work with for anomaly detection. And so to go from motion to activity, we do a number of steps. And the first one is that we'll aggregate in 20-minute time buckets. We don't care on the minute level what's happening. We take a step back and aggregate over these a bit longer time intervals. And so we just sum the motion values in these 20-minute time buckets together. And then the next step, and that's quite crucial, is that we apply a kernel to this value that basically feeds this, this motion detection into the future. So you can think of this that like when a person enters a room, that room will remain activated for actually up to 3 hours. Although the signal will quietly be reduced, it will remain activated for a much longer time. And this allows us to deal with the fact that when somebody enters the room and then is out of range of the sensor for a while, or is sitting down without moving much, the room will still be active. And so we'll typically do get a number of motion values every now and then. But because this signal is now carried forward, we get a much nicer continuous signal. And so what we did here at the top 2 graphs are just 2 motion intervals. And then we actually sum them together in the bottom graph, which is the overall activity pattern for that morning, for that specific room. Now, this is just for 1 day. Of course, we want to have a pattern of expected activity that is based on more than 1 day. And so actually the statistics that we draw here are quite simple. We'll just query the last 6 months of data that we have for this person, and we'll simply calculate the quantiles for different parts of the day. So the bottom of this light blue range is the 5% quantile. The thick blue line is the 50% quantile, it's just the median activity that we expect. and the upper edge is the 95% quantile. And so for every 20-minute time block, 90% of values are expected to fall within this range. Now, of course, if you would apply anomaly detection to this, which is quite simple, we just check if something is outside of the range. Of course, in 10% of cases, we would get anomalies. And so that would be way too many false positives. So we don't want to do that. But of course, we have more than one room. We have typically 6 rooms. And so in this example, with just 4 rooms, we can just look at the situation in multiple rooms at the same time. And only when the overall situation is alarming, then we'll send the alert, which gives us much fewer false positives. And so this is actually an example of where we compare that expected activity pattern, the colored bands, with the recent activity, which are the dots in these graphs. And so you can see that around 5 p.m., we actually have 4 20-minute intervals where the situation was alarming, because in 3 rooms, the values were outside of the expected range. In the beginning, we were actually struggling a bit with coming up with a good rule of how we should combine these different rules, these different rooms into an overall situation of alarmingness. And we realized that just using a rule like 3 rooms have to be, 3 out of 6 rooms or something have to be alarming, that wasn't working very well. Because we realized that actually some rooms are much more active during some parts of the day. And it makes much more sense to give more importance to those rooms at that time of the day. And so we come up with a statistic, which you see visualized here, which is that importance of different rooms throughout the day. And it's just like the proportion of all activity, which is expected to take place in that room at that moment in time. And so here you see that during the day, most of the activity is actually expected to take place in the living room and the kitchen. And so only when the overall situation is really alarming, then we'll send an alert. Okay, so that's for the anomalies. Now, I mentioned before that we calculate an expected activity pattern based on the whole history that we have of a person. Now, a first naive assumption that we make is that any day is basically the same. So we just take the aggregate over any weekday, and we come up with these quantiles. But what we found that is actually, if you look at the weekly pattern, is that that's actually a bad assumption. We typically see that on some days where a person comes in to clean the house or the grandchildren visit, that motion will be very different compared to the other regular days of the week. And so we realized that we should actually put those days separately as we aggregate to make this expected activity pattern. And to do that, we just applied some clustering techniques. So we just do agglomerative clustering with a certain threshold value based on the distance or the similarity between these different weekdays. And that allows us actually to split off these special weekdays. So this is exactly what you see visualized here. So the clustering algorithm was able to set aside this Wednesday, which is much different than the other days. And so when we build the expected activity pattern on a Wednesday, we'll actually only use data from other Wednesdays and not from other days of the week. And likewise, for the other 6 days of the week, we won't include Wednesdays when we make that aggregation. And now for those of you interested in the architecture, I added this slide. So at the heart of all of this, we have, of course, Python. It's Dockerized in a Kubernetes cluster running on AWS. Our sensor data lives in Timescale, which I'll dive into a bit deeper in a few minutes. Also, some part of the data is in Mongo, some summary stats. When there's an alert, we'll send the HTTP post request to the Jane API. We have our logs sent to Grafana. We have integration with Sentry. which was really it's really nice, so that we get notifications in Slack whenever our code should crash. So that's a really nice thing to have. And yeah, in addition to that, we have Circle CI integration with GitHub. So that's where our tests will run before we deploy. Okay, so 5 more minutes into Timescale specifically, because that's indeed where our sensor data lived. It was the first time for me working with this technology, but I had a good experience, so I decided to share. Timescale DB is an open source database. It's built on top of PostgreSQL, and it's specifically for analyzing time series data. And if you want to use the power of Timescale, actually you just have to, well, first of all, activate the Timescale extension. It's just an extension to Postgres, and you can create what they call hypertables. And as you create these hypertables, they're just regular tables, but a requirement they have is that you put timestamps in the index. That's really crucial because it will allow Timescale to optimize stuff in the backend. And as soon as you have these hypertables, you can actually have all these nice Timescale functions now that you can apply to that table. And without any more effort, the backend will be optimized for writing and analyzing time series data. So one of the tricks they do is that because the data will be partitioned inside the database, but because they know that they have the timestamp in the index to partition by, and because they know that typically with sensor data, all the writes will happen with recent timestamps. You won't be writing data from months ago. So because it has that information, it's actually able to keep those really hot chunks where you're going to write to in memory. And so you get really fast writes there. So that's nice. In addition to that, you have a ton of other optimizations under the hood. Some of the functions that I mentioned, the Timebucket function is really something nice, so that you can really just create an interval of 5 minutes here where you can then group by. So in this case, you'll have per 5 minutes in each location, the last temperature for the last 2 hours. Really convenient. And the last function is also Timescale addition to Postgres. And finally, I would like to sketch out another part of Timescale that we used, which really allowed us to solve a question that we got from the front-end guys. So they wanted to visualize this kind of stacked bar chart in the front end. And the data that they needed was, so just the raw motion values actually per hour for each room. That's the request that we got. But we realized that this data really has to be up to date, because if the query would only run each hour and people would check the motion of their loved ones, and they find out that the last couple of hours it's really low, they would panic, right? But it would just be our data lagging behind. So that's a situation you absolutely want to avoid. And so we gave this a thought, and we decided, because we want to be a real-time, we would like it to just run inside the database. There's no fancy integrations there, so we can just keep it really simple, a simple data pipeline. And because also the request they got was actually quite simple to create this kind of data set. And so we decided to just do it in SQL. Okay, now, for those of you who have written some SQL queries, you may know that they can actually get quite long and ugly the more complicated stuff you want to do. And so you can create this beast of a query, and one solution to this problem, the fact that it's long and ugly, would be that you just create a view. So a view is just that you give this beast of a query a name, and from then on you can just use that name as if it were a table, and you can access it in other queries. So it has the advantage that it's now shorter and much concise. You can build pretty queries using that view, and you can use it anywhere in multiple queries, so it's more reproducible. So that's nice, but the problem is that every time you fetch that data, it will actually run the full query in the backend. So since these queries can be slow, it's really a bad idea to use a view for something like this. Now, to solve that issue, you can actually use materialized views in Postgres. Materialized views, they're not so much different, but each time they run, they will actually save the result to disk. And so they will only refresh or update when you ask them to. But since the calculations have run, you just have to fetch the data. You just select the data from the materialized view. It's actually just like a table, and it's much quicker. So that's nice, but there's still a downside to this, because you need to write code to refresh these materialized views. So that's an added burden. You have to write and maintain that code. Plus, specifically with time series data, actually to create a visual like this, the older time blocks, they'll actually remain kind of the same. The old data won't change anymore. So you'll be recalculating a lot of stuff that will actually in the end remain the same. So specifically for time series data, you can actually do it more efficiently by just recalculating the new stuff. And so in Timescale, you have continuous aggregates, which allow you to, they're just materialized views, but you can set this updating policy as you create this table, this materialized view, basically. In this case, we chose to put it every 2 minutes. And it does efficient aggregations. Because of this time series indexing, it knows to only look for changes in the last few chunks. So we measured the performance. It was way better than you would have with the standard approach. So that's actually my talk. I would just like to give a shout out to the Jane people that I worked with. Really fun guys to work with. Great team. And thank you for your attention. All right. And now I'll be available for, should I stop sharing my screen?
You just, Chris did it for you.
Yeah.
Okay.
It's okay.
Normally we have a big round of applause. I feel like we need an applause machine or something, but let's just.
Okay, thanks.
Yeah. Thanks, Jeroen. That was a very interesting talk. I think we already have 2 questions from our viewers. So let's start with that. And if there are any more, just pop them in the chat, and we're keeping an eye on it. So first question, let's see if I can find it again. Someone is asking, or a lot of people are interested in the difference between InfluxDB and Timescale DB.
Yeah, I'm afraid I won't be able to provide a good answer here because I haven't worked with InfluxDB. So if you have, I would definitely recommend looking into Timescale as well. Just put them aside and then let me know. I'm very much curious what you'll find. To me, it was something like, maybe I didn't mention yet, but at Faction, we are not just machine learning people. We also have just really good software developers. They actually came up with this technology. So I'm just more from the user side. And I just, as a user, I enjoyed it very much. And so that's why I decided to share. I do think we have a new question.
Oh, nice.
Coming up.
Oh, we have one from Islam. So how do you oh, wait, I skipped one. Sorry, Peter, you were first. What are your plans for scaling the number of users of your platform?
Good question. Right now, it's actually quite okay for the foreseeable future, because like the slow analysis, which is building this expected activity pattern, which takes a lot of data for up to several months, that only runs once a day, so it's quite manageable. Whereas the analysis that runs every 20 minutes, which is to check the recent activity, it only fetches a few hours of data per person. So it's actually quite performant. Like, we were keeping close track of this, but usually like this, within, after a few seconds almost, this analysis is done. So something we're keeping an eye on. That's also one of the things that we constantly save to MongoDB, like all the statistics of the different parts of the analysis, how long they're taking. But so far, it's quite okay.
Cool. We have a lot of database enthusiasts here today because we had someone giving us the fearful emoji as well when you mentioned MongoDB. But let's not get into that.
We all use it for small. It's on the side.
So now I think it's Istvan's turn, unless I am skipping someone else. I hope not. Istvan is asking, how do you generalize this? Because he thinks there's a lot of variations across households and elderly people.
Yeah, so maybe I wasn't clear on this, but the expected activity pattern is already on the household level. So each household, each customer has its own expected activity pattern. We have been thinking of looking for similarities over customers, but we haven't gone into that yet. It might allow us to send alerts earlier on, because right now, one of the challenges is that we need like 25 days at least of data collection before we can send meaningful alerts. If we would be able to notice early on that, okay, we have this pattern, and from all the other users, we know that it's gonna be more like this, then we may be able to already after 10 days or so send or activate the alerts. But yeah, for now we haven't gone into that direction.
Okay. Well, in Istvan's name, I'm thanking you for that very clear answer. We have 2 more questions already. Pablo is asking if you had any labeled data to validate your model.
No, that's one. We don't have any labeled data of people not reacting anymore, things like that. But we did do an analysis, and that actually connects to the next question also, which is from Peter Kusma. If 20 minutes isn't slow to react, if something would happen. We actually did a simulation where we implemented what we call full motion stops on the raw data. So we just took a full day of data, and then at some point we said, okay, now all motion stops. And then we applied the regular algorithm and saw how long it would take before the first alert was sent. And typically it took about 2.5 hours for the first alert to be sent. And you may think it's not great, but I've heard stories of people just being on the floor for a full day. And that's quite of a common emergency situation that you can have with an elderly person. And so we can definitely cover those. We also have the SOS button in case they're capable of just alerting it themselves. But because of the fact that these motion sensors, and actually I don't see any other sensors except for if you start to measure the vitals themselves, you don't want to have something that sends way too many false positives. So you have to wait for some time to be sufficiently certain. Others, every time this person takes a nap during lunchtime or something, you might start sending alerts, and we don't want that. So we need some time to be sure that something's up.
And we have a follow-up question then. Is there like some plan for the future to maybe implement a kind of feedback loop where the alert is not triggered to the family, but the elderly person gets like a phone call or something, and if they pick it up, the alert goes away and everything's fine, but if they don't, then it's escalated?
Well, we do have a number of testers, some volunteers, some people who were paid to test the solution, and so they will actually provide feedback if an alert was sent and it wasn't good, and then we can go look into data to see what actually was wrong, what we missed. But this is a part of the solution that I was actually not too much involved in, but I do believe that if you send the SOS button, that actually there is a person who will directly call. So it will show up in the person's smartphone of the child of this older person. But I think we also have an emergency central that will just call them directly to check if everything is okay.
Might be interesting to use that for training as well, I'd imagine. But
yeah.
So Istvan is asking if he can apply this to his teenage sons. Sure, Ethan, why not? There's an app from Google for that. You know, you can just monitor them anywhere, anytime. Okay.
Yeah.
So if we don't have any further questions right now, let's give you another hand. And then,
You're welcome.
Chris, I suggest you bring up Victor's screen and we can continue with the soccer analysis.
Yep. All right, Victor, I think the floor is yours.
All right, perfect. So if everything went well, you can now see the screen. So thanks again, guys, for tuning in today. My presentation, I'm from ML6. My name is Victor Sonk. I'm a machine learning engineer there. ML6 is also a consultancy company in machine learning. So, but today I'm going to talk about one of these cool use cases, which is video analytics for soccer games. Now, we had a customer come to us with a question, and that was actually ended up one of the coolest things that we did. So I'm here to talk about this for you, and I actually hope, because it's a lot to cover, so I hope I can crush it down into 20 minutes and make it interesting. So meet our customer. Let's start there. We're going to go through the journey of what they wanted and then how we got to where we made it. And so our customer is an international player in the sports business, right? So traditionally, they were known for broadcasting big events for television, like Sporza is in Belgium. And now, looking for new business opportunities, they were thinking of like we have a lot of these cameras that are attached to a pole in the second, third, or fourth divisions of soccer games, right? And so what they did was they sent out this 180-degree field of view camera image, and they streamed it over the internet so that people that know the players could tune in. But obviously, they didn't have the budget in these kind of ligas to actually produce, to make the stream interesting, to zoom in when a goal happened, to do things like that. So they were thinking, okay, maybe we could use something like machine learning for this because it would go automatically. And so that's what they ended up coming to us for, is the requirements. So we had to design and create a platform that can handle auto production and broadcasting for up to hundreds of games per weekend with as little time delay as possible. So that was the main question, right? And we can immediately see that's quite broad. And also we had about 3 months to do this with 4 people, so 4 full-time equivalents. And so if you look at what they're asking, you can basically split it up into 2 main parts, right? The biggest part, the first part is auto production. So with auto production, I mean, how are we going to make the stream more interesting, just like it was going to be on television, right? If there was an actual streaming team behind it that edited the video as they went. So can we make that live with machine learning? And so the first part of auto production is the player and ball tracking. So obviously, everything you're going to have to do is going to start with knowing where the players are, knowing where your ball is. And typically, that's something you can do per frame. So the people that have already dabbled in machine learning, they know very well that an object detector can do this frame by frame. It's not very hard. So that's what we ended up doing. We implemented a object detector that could detect people and a sports ball. Now, we did this on 10 frames per second. Just to keep the load down, I'll show some numbers at the end of the presentation, but it was quite large. Also, it had to be streaming. So let's take it 10 frames per second. It should be plenty. And then on each of those 10 frames per second, we can just detect it through the object detector and get all the positions of the players and the ball out of it. But then there is a second part, and that's event detection. Now, remember, these are second, third divisions of soccer games. So they really, like some of them just start on a schedule and they're probably way late of that schedule. Like you probably all know your regional football club. So one of the things that we had to do is detect when the start of game actually happened, because usually the stream started when the match was supposed to start, or 10 minutes before. But obviously, in these lower classes, it wasn't always going to go according to plan. So sometimes it was even an hour before you could actually see the match. And so to give the people watching a ping like now the actual game is starting was already a big win. And then you had, for example, an event like a goal or a corner or a foul that you wanted to detect as well. But these things are typically handled in sequences of frames. Like if you take a tackle, for example, if you take a freeze frame of any of these frames, it's hard to determine what is actually happening. So any of these events, you actually have to take into account all of the frames around it. So we have to actually window and then take that window into account and put it through the machine learning model. So again, we had 10 frames per second, and we took the window at 3 seconds. So that's 30 frames. We bundle them together and we send them through, but we offset them per second. So every single second, we get a detection of a goal of a start of game until the start of game actually happened, of course. And so that way we send it through. So we had to build in a windowing functionality as well. And then there is a second part of the requirements. So again, design and create a platform that can handle auto production. Okay, sure, the auto production, let's do those 2 parts. But then broadcasting for up to hundreds of games per weekend, which as little time delay as possible. So first of all, that requires us to support streaming, right? With as little time delay as possible. I think they were talking about that FIFA does it in under 30 seconds. So we had to try to keep under that as well. That is the latency between the actual event happening and what we output. And it had to be highly scalable. So if there is a weekend with hundreds of games, it should perform as well as a weekend with 10 games. And then it should be easy to host and interact with machine learning models. The main idea behind that was that you could then scale it out to other sports as well, because usually detecting players is the same for soccer as it is for basketball, depending on your training data, of course. But the idea would be that, okay, if we can take those 2 apart, that would be really nice, because then we have a nice modular architecture. So try to keep the architecture as generic as possible. That was the main idea. So this was the solution that we came up with. It's actually a relatively generic streaming idea, but I'm going to talk over each part because I find it interesting how it ended up together. So first of all, we have the Google Kubernetes engine. I think most of the people that work in this branch have already used it or seen it. So we use Google Kubernetes engine to actually transcode the video. So we got a live stream in, transcoded it, get the frames out so that we can get 10 frames per second. We published it to Google Cloud PubSub. So everything today is going to be Google Cloud. But in this case, Google Cloud PubSub is basically a managed version of Apache Kafka. So we published the frames on that. And then the heavy lifting is done by Google Cloud Dataflow, and again, Google Kubernetes engine. Google Cloud Dataflow is based on the Beam model, and it's actually going to do all the moving of frames around, right? It's going to do the pre-processing, it's going to do all of these things. And then the actual machine learning models are going to be run on Google Cloud Kubernetes engine. Then we stored all of the things that we did in Bigtable. Bigtable is a managed version of Apache HBase. It's basically a sort of IoT database that can handle a ridiculous amount of writes at the same time. So the idea would be that if we have streaming video going in from hundreds of games per weekend, we might as well go for the big guns. And then we have the Google Kubernetes engine again, just to host the video player as a debug, as a way of debugging. So let's start with the transcoder, the easiest part, the most fun part. Everyone that has ever done anything with video already knows FFmpeg. FFmpeg is everything you need, is the Swiss Army knife in terms of video. So FFmpeg could just could read the HLS stream that we got in from the customer, and then we just use the code that you see below together with Asyncio to make it work asynchronously, and so it just captures the frames at 10 frames per second, and it dumps that to the output, to the stdout. And from there, we can just basically grab the bytes and push them to Google Cloud PubSub. So that wasn't actually a very hard part, and thanks to FFmpeg, that's all possible. So if you ever have to do anything with streaming, it's FFmpeg all the way. But then let's talk some data crunching, right? So this is where the actual magic happens. I skipped Google Cloud PubSub because it's just a buffer. There's nothing sexy about it. but Google Cloud Dataflow and Google Kubernetes are very sexy indeed. So to compare them a little bit, let's start Google Cloud Kubernetes Engine. We hosted our machine learning models on that to get the predictions, mainly because you could choose different node pools with different specifications based on what model you needed. So for example, the object detector needs quite a lot of GPU power, while, for example, something like the start of game might not have to. So you could basically change what resources you put on each model, and it also makes it very modular. One other nice thing is that you can expose these models, these APIs on Google Cloud Kubernetes Engine to Dataflow via an internal load balancer. So that means that if Dataflow is receiving more and more streams, it will start to ask more and more of Google Cloud Kubernetes Engine, and that will spin up more workers. And also, it's only reachable from within the GCP project, which for security reasons is quite nice. And then to actually process the video frames, we used Google Cloud Dataflow. For those of you that have not used Google Cloud Dataflow before, it's mainly a large distributed parallel computation cluster that can handle a lot of computation just as a standard Beam model. And so the main reason that we went with Google Cloud Dataflow is actually because they have this really neat thing in which they can allow you to window frames or to window objects, basically, that come in out of order, and you can window them even in streaming mode, which is really, really useful for us. Because remember, all of the events were done as a packet of 30 frames. So they had to be in order and windowed. And also Apache Beam, again, it scales as it detects higher workloads. So that was kind of nice that you don't really have to think about that. It's managed. And then getting predictions from the machine learning models. Take into account this was a while back. So back then, we didn't have AI platform yet. The people that know Google Cloud, they know that AI platform is actually quite good now. Back then, it was ML Engine, and it had a lot of limitations. So we ended up using Google Kubernetes Engine mainly because you couldn't actually use GPUs at a time or workers with a GPU as serving workers in ML Engine. So that was already a big deal because if you have a decently sized object detection model, you really need those GPUs. And also there were restrictions on traffic. I think you could maybe send like 1.5 megabytes tops at the same time. So that was just not enough. But right now, if you want to do something similar and are working on TensorFlow, you should definitely check out AI Platform because it's the managed version of this, basically. The Google Cloud Kubernetes Engine gives you more flexibility. And then a little more zoomed in on the pipeline. So on the actual, how does this Google Cloud Dataflow, what does it look like? Now this will come as maybe a little bit of information too at the same time, but I'm going to go through all of them, and I hope you can follow to make it interesting. So reading from PubSub is simple, right? You just take it from the buffer, but then pre-processing. What does pre-processing entail? Well, one of the main things we had to do is above you see one of these 180-degree images, right? These are fine, but if you know object detectors, you also know that they usually scale down your image quite a lot before they get sent through the model itself. So if you do this with this kind of picture and you scale it down in the way an object detector would do, all the people would be squished, and the object detector would not really quite do well. So what you probably want to do is you split it up into 5 parts or more, and then you basically send them through as a batch. You could have overlap so that you can then restitch it together later. But the overlap wasn't that big of a deal because people are moving all of the time anyway. But you definitely have to chop it up. And if you chop up these images and you send each of these images through the model, you get much better detection results, but it takes a little bit more time to process. So we ended up doing 5 cuts, I think, and we pre-processed that in Google Cloud Dataflow first. Then there is a prediction step, but not only do we have to do the prediction step, we also have to dewarp and rewarp. So the moment the frames come in, they get chopped up into 5, they get sent through the Kubernetes hosted models. The models send the location or the bounding boxes back. At this point, you know the position of each player in the field. But as you can see, this 180-degree image is actually kind of warped, like you would have in a GoPro, for example. It has this fisheye effect. And I think I have a pointer here, yes. So you can see here that the bottom line is actually curved, and we don't want that. So the first thing we had to do was get rid of that curve and de-warp it. So then you see here that it looks kind of strange, it looks wrong, but you can see that the line below here is now straight, and all these lines are perfectly straight as they should be. So the fisheye effect is taken care of, and then we just do a relatively simple perspective transform that takes the 4 corner points of the fields and then projects it into the dimensions of an actual football field. Fun tip, actually, a football field doesn't actually have standard dimensions. There is quite a lot of slack on it on what you can allow a field to be in terms of size. But in the end, yeah, we came up with this. And then if you take the bottom coordinate of your bounding box and then project it through these projections, then you actually end up with the XY coordinate of your player where it touches the ground on this field, allowing you to make a mini map, which is quite nice, and also keep track of things like how far they run and stuff. And then we go into the first event. So right now we have the player and ball positions, and then we have the first event. And the first event is start of game. So the first thing you have to do is window it into sliding windows, right? As I said before, you need multiple frames to do this kind of thing. And one of the things that I want to say that we struggled with at first was that if you use streaming windowing in Google Cloud Dataflow, it will basically say, I'm not going to assume that all the data is going to be on time always. So what it does is it uses a watermark, which basically says if I have 29 of the 30 frames, I will already process this batch, put a watermark, and then if the last frame comes in, we can recalculate that batch and send it through again. Which is fine, I guess, for things like bigger things. But we were counting on the fact that there were 30 frames in there, because otherwise the machine learning models would complain, right? So you can use a trigger instead of a watermark. You can use trigger where applicable to actually wait for that 30th frame, because we know that there should always exactly be 30 frames in the buffer. So you can use triggers for that. And then there is another thing. For people that have used Google Cloud Dataflow before, they might know, but what's your parallelization key? So the main thing is that Google Cloud Dataflow parallelizes your workload based on the key. The key is the unit of parallelism, so nothing else, right? And at first what we had the game ID as the main ID, which basically meant that if you use the game ID as the key, that Google Cloud Dataflow will just say, okay, everything with the same key will be run through the same worker. So we had a whole game being processed by a single worker, which is just ridiculous. So just adding things like a timestamp or a frame ID, frame ID can just can move the parallelization key from your game to your window, or even to your frame, or even to your timestamp, and that just distributes much better. So it's in the paper, actually, that's where we found it, but you should read the paper. And then there is one more thing. I mentioned before that you could auto-scale these systems, but with some of these models, it was actually quite difficult, mainly because GPU workers actually depend on the NVIDIA drivers, and these are huge beasts. So that means that your Docker containers are actually going to be very, very large, which means that the moment workload comes in, Google Cloud Dataflow starts to spin up workers. Google Kubernetes Engine starts to spin up workers, but these workers take quite a lot of time to spin up. So at that point, a certain backlog is building up and building up and building up. And at that point, it's going to overcompensate with too much GPU workers. It's going to overcompensate, so it's going to go over what you usually should need, and then work down this backlog. And this was incredibly inefficient, especially in the beginning of the matches. So we got rid of that and basically said, okay, we know when a new game is starting, and a game is just more frames, right? So we actually have a relatively fixed demand per game, so we know how much workers to spin up if a game starts, and that's how we ended up doing it. And then I have a little demo of, in the end, what it looked like. So all of these components, I hope you were able to follow so far. So all of these components together actually end up like this. This is the player at the back end, so at the Kubernetes engine. So, let me just, yep. So you could see you have this video here, and then the first thing you obviously can do is change it so that the players are like the players and the ball, the action is followed, which is already quite a lot more engaging than just the 180-degree field of view. And then you can also see the different players, their teams, the minimap, and the position of the ball. We also managed to do the team detection completely unsupervised, as well as getting the keepers and the referees outside of these clusters. So thank you for listening, and I hope that you were able to follow.
Thank you, Victor. That was very interesting, at least for me. I have some experience with data flow, but I've never explicitly set my keys. So you've just made me go to Bitbucket very anxiously that I've been doing it wrong all this time. So same as for Jeroen, let's give our second speaker a hand of applause. Okay, so everyone in the audience, please get your questions ready. I have a first one for you.
Mm-hmm.
Is it Kubernetes or Kubernetes? I cannot figure it out.
There's many different ways to say it. I say Kubernetes, I think, most of the time, at least.
Most of the time you do it, yeah.
But I think I switch even constantly. So I'm actually not sure. I'm actually not sure. I've been seeing talks of people that work with this professionally, and they are not even consistent in what they use. So it's at least it's less bad. I know I have a colleague that actually calls it Jupyter notebooks, which I think is a lot more controversial than Kubernetes.
Interesting. Yeah. Okay.
Well, but the Jupyter thing makes sense, because Jupyter comes from Julia, Python, and R, right? That's the Jupyter.
Yeah, but they were meant for it to be pronounced Jupiter.
Yeah, I know, but anyway.
Doesn't matter.
All good. Okay, so first we have just a general tip from Bart Hamers, who says that we need to check out the research done by Jesse Davis at the KU Leuven. Sure you've heard of him, or maybe you haven't, then you should definitely look him up.
I'm writing it down.
Good. And then the first question from Bruno. Hi, Bruno. Who's asking, how did you deal with the different distortions for the many types of lenses that are taping a soccer match, I assume? He says it seems very non-trivial. Okay, cool.
Actually, it wasn't. So what you usually would do is you have like a sort of checkerboard as an example, and you go to the camera. The checkerboard gets distorted, but you know how a checkerboard should look like. So that can allow you to give you a calibration matrix, which can dewarp everything that you need, right? But they had hundreds of cameras out there already, so we couldn't really do that. And we also didn't have a camera on hand that we could do it on because, and that's a good thing, all of these cameras were the exact same cameras. So in the end, it wasn't that bad. And what we ended up doing is finding, by trial and error, I actually managed to find a script. I don't know who's it from again, but I managed to find a script that could do it based on two parameters, on basically two parameters of the camera itself. And then we trial and errored it until we found the two parameters that, okay, like this dewarps the image that we need within reasonable margins. And then we could basically apply it to every camera. But if you really want to do this on much different cameras, you should definitely do the calibration step first. And I will just give you a matrix that you can use to dewarp the image.
Okay, cool. Thank you. Then we have a second question from Michael or Michael. He says, it sounds like the kind of project that's kind of easy to do in terms of machine learning, but the main challenge is the engineering. Can you comment on this?
Definitely. So yes, that is true. thanks to the beauty of all of these open source machine learning models, this was definitely not very, very hard to do in terms of machine learning. Definitely the object detector, right? It's just a retrained YOLO. Because back then I was the best. Right now I would use probably something different, but like that was relatively easy. But it's definitely the fact that it's streaming, that it's so much. Actually, I have some auxiliary slides here just to give an idea. I think my screen is still shared.
Yeah.
So just to give an idea, we had the 10 FPS, right? The 10 frames per second, 90,000 frames per game on average, at about 3.25 megabytes per frame. That gives us about 300 gigabytes of processed data simply going through the pipeline per game. And remember, we had to do hundreds of games per weekend, right? So the sheer size of the data that we had to manage was definitely the bigger challenge here.
Cool. I'm very jealous of Jeroen right now because I see he's just gone out for a pint and mine is completely empty, and I didn't I didn't bring a
cheers anyways.
prepared. I think I'm gonna do the same as you in a second. But let's first finish the questions. So we have another question from Kevin, who is asking if you always have a camera that captures the full field.
Yes. So that was a nice thing. We did have a camera that did the whole field. The downside of that is, and I can actually show it as well, is that first of all, never trust your data, right? So this camera wasn't always attached where you thought it was gonna be. There was nothing that you could assume. So at first we assumed, for example, that the middle of the field was usually where the camera was at, but you can see down here that it's definitely not the case. And then there was, for some reason, there was an ice hockey field in between our data set. So yeah, that was definitely, and here you can actually see the different cameras that were attached to the rig, let's say, but they weren't stitched properly. So yeah, it was, while you always had the whole field, it was sometimes more difficult than you thought. And also, what I want to mention is that usually these lower classes of soccer clubs, they don't usually have the broadband necessary to send relatively high quality video. So that means that if you want the frame to envelop the whole field, you actually suffer in how far, like the detail that you have still in your image. So that was sometimes we had issues with that the players even zoomed in, even with the crops. Players all the way at the back were sometimes very hard to see. But the idea was that if you could do it for like 80% of the fields, that's all right.
I think that ties in
what they have now.
Sorry, I think that ties in neatly to the next question from Henrique. He says the ball is quite small, so did you use only object detection to track it? Just increasing the resolution to solve the problem? Or how do you deal with occlusion by players or out of frame issues?
That's actually a good question. So at first we trained it. Basically, we first looked like what can a pre-trained object detector do, right? And a pre-trained object detector in the Coco, if you know the Coco dataset, there's actually the class sports ball in there already. Now the good thing is that those sports balls are usually actually tennis balls. Even how do you say, baseballs. So they were already actually calibrated to be quite small, but even still we had issues when the ball came all the way at the back. So what we ended up doing is, labeling 700 footballs at the back of the field and retraining the model with that. And then in the end, we got more professional labeling and actually train it a lot better. So in the field, it was actually quite good because it's pretty easy to see a ball on a green field. But the moment it was in the air, it was usually not very well to see. So then you have two options. Either you accept this and say, okay, we don't really need to have the ball all of the time. Like if we know where it last was and we have the positions of the players, we can usually know where the action is going on relatively well. Another option would have been, and that was one of the things on the roadmap, is tracking, object tracking. The problem with that is that object tracking requires a state, because it needs the different frames in order but also from before those 30 frames that we used in the end. So that makes it a lot more difficult to do this in the streaming pipeline if you have the bottleneck of this tracker. So in the end, we ended up just having a better trained object detection model, and that performed quite well with some extra rules.
Cool. So the next two questions I think we've already covered. Joss is asking if you use a pre-trained model like YOLO, and the answer is exactly YOLO.
Exactly
and
YOLO.
then Henrik is asking when there is a switch of cameras, if there is an extra delay, but it was always the same camera, right?
Yeah, it was always the same camera.
All right.
Or the same type of camera, right? And on different fields.
Pablo is helping me. Kubernetes, or I could have done this wrong, comes from the Greek word for so it would be pronounced Kubernetes. Kubernetes.
Okay.
Nates? This has
okay,
only made it worse, but still, thanks, Pablo. But
so Kubernetes, I guess.
We have a business question from Rui from Portugal at that. Who are your customers, football teams, the betting companies, both?
So fortunately, that's my personal opinion. We were not running into betting companies yet. But yeah, I mean, it's hard to deny that it can be used for that. But the main customer was actually the sports broadcaster, so the actual owner of the cameras, right? But we have had very similar questions from relatively rich clubs to more soccer broadcasting customers like this. So those are the kinds of customers. And now actually in Corona times, there's a lot more demand for it because people can't go to the football matches. So yeah, it's a cool project to have now.
Cool. Kevin is asking a follow-up question to his first question. How would you handle not having, I think it was the single camera? Makes tracking a bit more complicated. Do you have any insights on that?
Well, I'm not completely following. So how would you not handle not having this? It makes tracking, etc., a bit more complicated. What do you mean with this?
I think he means the same camera always. Trying to.
Okay. I think it should be relatively okay because the object detector is actually quite robust to these kind of changes. So if you had if you have a moving zooming camera, okay. So if you have a moving zooming camera, that makes it quite a lot harder. Then you definitely cannot use a tracker, right? So that's already out of the question. But if you have people going in and out of view, it makes a lot of things a lot harder, right? But in essence, if you have a moving camera, that means you have a person that is already directing the action. So at that point, that's not what you're looking for anymore. What we really built is basically doing that exact thing, is trying to figure out where you should look at. And the nice thing is that you can then use some things like how far did each team run, for example. That's a nice side effect of that. But if you already have a person that guides the camera and it's zooming in and out already, it's a complete other question.
Cool.
I also see that there is someone asking for the Google Cloud billing report. It was high. It was very high. So I think at one point we did a small test just to see that the whole thing is running properly, and I think it cost like $1,500 or something. So yeah, it was a big pipeline.
Yeah, and I remember looking into Bigtable at some point, and like the minimum cost you can get it at is $1K per month or something. Yeah,
because you have to at least have 3 workers to go into production. I think you can do it with 1 if you're not going to production, but if you want to do production, you have to have 3, and those are expensive workers. So.
Okay, so Pablo has given us clarity on the subject. It is Kubernetes.
Okay.
Right? Let's hope. Okay, and then the final question is from Maxime. He's asking if you tried your model with a different game than football, and was it any good?
That's actually a good question. No, we didn't, simply because we didn't have any data for it, apart from this hockey game for some reason that was in there, but we didn't try it on that. But I would think that the setting that we use, so the generic streaming architecture that we use, is actually quite interchangeable. So for example, the player detection is something you can just take over. Maybe it would be hard with ice hockey with the whole harness and things. I think the base building blocks should be fine. But then, yeah, of course, on every game you have other rules. So all the event models, like scoring a goal or making a foul, are by definition going to be different. So there is only so much that you can reuse, but the whole, like the big part that we talked about before, like the actual difficult part, the engineering, is reusable. So the whole streaming pipeline is relatively generic.
All right, cool. So I suggest we give Victor another hand of applause here. Small hand of applause. Thank you so much. And then Chris, I suggest we switch to Benjamin's screen.
Yep.
For our third presentation. Meanwhile, I'm gonna try and get someone to bring me a beer.
Good luck with that.
That sounds like a great idea. It actually sounds like a terrific idea. Hello, so my name is Benjamin. I work for InterSystems and also for a company called IKNOW. And getting another beer is a terrific idea because I usually don't present to as highly qualified an audience when it comes to data science and NLP. So feel free to calm down, sit back, and I hope I can make it a little bit entertaining after these truly spectacular sessions by Jeroen and Victor. Okay, so what are we going to talk about? You might have heard about InterSystems. I'm sure that Herman definitely has. InterSystems is a global company that sells data platform technology with a big footprint in healthcare, and in Belgium we happen to have a bit of a more varied mix, also including some public sector and retail. But this session is not at all about InterSystems. It actually is about IKNOW, which goes back almost 20 years, when it was founded as a small Belgian startup focusing on natural language processing. And much of the rest of the history of IKNOW is actually on this meetup. So Christophe worked for IKNOW in the first decade episode, if you will, and then in 2010 we were acquired by InterSystems. That's just a little after I joined. Not that I had anything to do with it. Herman did have something to do with it. But we were acquired by InterSystems, which gave us a much broader platform. It also allowed us to embed our natural language processing technology in a data platform and sort of broaden to a much larger set of languages. Anyhow, that's a little bit of history. Let's get into what IKNOW actually is about. So the core task of IKNOW is to identify concepts and their context in natural language text. What do we mean with concepts? What do we mean with context? What do we mean with natural language text? So that the idea of IKNOW is to identify not just the raw words in a sentence, not just to put it into single word tokens, but identify those groups of words that actually belong together because of their role in the sentence. The words that together represent a concept as it was coined by the author of the text, and also get the linguistic context of those concepts from the natural language sentences themselves. Why is that important? It is important because many of the classic brute force approaches don't give you all of the detail. And when I was just browsing through this again, I suddenly got afraid because people might realize that this is actually a fairly old slide, a fairly old screenshot, not because you might read the date at the bottom left, but obviously everybody can kind of relate to the date of the trending story at the time when I took this picture. But that aside, the classic approach to kind of making a sentence like this usable for data science, usable for machine learning, is to translate it into a word vector, for example, where you have you take all of the words in the sentence and you give them a frequency, and that's sort of your value. So suddenly your text, which was natural language, which was totally unintelligible for an algorithm, has become a vector that you can add. You can take the average, or you can do all sorts of numeric processing, algorithmic fun with a sentence once it gets into this form. However, this is a totally different sentence which happens to have the same form. So this is a bit of spiel, of course, but the idea here is that by going to that word level, you're losing a lot of context. So what you actually want is to identify not just look at the word token level, but have tokens that represent the concepts that your text is actually about, the concepts that are used in your sentence. And this is often referred to as n-grams, so monograms are single words, bigrams, trigrams. So the idea is to identify those and sort of have a vector with frequencies that represent those concepts, that represents those n-grams, and then suddenly it's a lot harder for wise guys to make funny sentences, because if you keep Bank of Japan together, if you keep Fed announcements together, if you keep world stocks together, it's hard to kind of distort the meaning of your sentence. So that's why these concepts are relevant. And then context means, how do those relate to one another? Is there any sentiment or negative or affirmative context to these concepts that might also be relevant to take into account when you're processing the text? Okay, how does it work? So the brute force to identify these n-grams, to identify these meaningful n-grams, is just use the power of statistics. I assume there's a fair number of proponents of that on this meetup. So imagine this: we look at this sentence. So we take all of the monograms, we take all of the bigrams, we take all of the trigrams, and then through the sheer force of numbers, we'll find out which ones are most important. So you can use metrics like TF-IDF, term frequency, divided by the inverse or multiplied by the inverse document frequency, to kind of find out which ones are most common, but also not too common, and that will help you identify some. Another approach that sort of takes the same starting point would be to use a dictionary to prune all of those possible n-grams that you would find in a sentence, and only keep those that actually make sense because of their because, for example, it's an adjective and a noun, or because you know that these words often belong together. That's definitely an effective way of working if you know the domain that your text is about. But if you don't, it's sort of hard work. So the approach that we take with INO is a bottom-up approach, where we're taking the language and nothing but the language and start from there. So rather than trying to identify those noun phrases, to use the part of speech tags that linguists often refer to rather than try and identify those noun things, the congressional hearing and the EpiPen price hikes, we look for all of the things that are possibly not part of those noun phrases, because it's those noun phrases that are usually very typical for a domain and therefore hard to build a dictionary for, or tedious or costly to build a dictionary for. So what we'll do is we'll just tag all of the tokens that possibly are a non-concept. Then we'll apply a bunch of very complex disambiguation rules, in which we sort of go from ambiguous state to a less ambiguous state to a lesser ambiguous state until we arrive at our sort of binary classification of tokens that are either a concept or a relationship. There will also be tokens that we didn't know about, that weren't in our list of potential non-concepts, but they are sort of by definition concepts, because they're not a potential non-concept. So once we found all of the relational elements, we'll by definition have found all of the concepts. We'll have found those n-grams that sort of capture meaning, capture something that the author really cared about and put into his sentence. So this pattern, this sort of looking at relational elements that sort of separate the different concepts in a sentence, that's sort of at the core of our bottom-up technology. So that was patented as Belgian technology almost 20 years ago. That's what InterSystems bought and then started to embed into their platform. And that's what we still believe can add value in a variety of use cases. So Remember, the goal was to identify the n-grams that made sense, so the n-grams that would be good tokens to include in machine learning or to include in exploratory or search interfaces. Brute force was first, a very fast approach. It's obviously very simple to implement, and the statistics often work out. They sometimes depressingly, they're sometimes depressingly effective if you have enough data to work with. However, they can be computationally expensive. There's no interpretation level to it, so a ranking like TF-IDF or BM25 might tell you what's relevant based on statistics, but it won't tell you what it means. If you're looking at dictionary-based approaches, you get that interpretation level because you bother to compile a dictionary, so you could as well link it up to some an actual ontology. For example, in the healthcare domain, there's a bunch of very important or industry standard ontologies that you might map your text to. Also works with getting volume and it's very accurate, but it obviously comes at a very, very high maintenance cost, especially if you start looking at proper nouns of people, of places, etc. Starting to put all of those in a dictionary is a fair task, and it's also constantly evolving. Now, a bottom-up language-based approach like INO can also be very fast, well, ours is, and very accurate, and also, more importantly, it works with any volume and any domain. And it can also kind of on the fly get to some additional linguistic context. However, it doesn't have an interpretation level out of the box either. Okay. Besides the concepts, we also try to identify some context because so that's this is also in a natural language world. When you're building parse trees of your sentence, we don't go to that length. We don't build entire parse trees, but we have this sort of binary cutting up of sentences into concepts in blue and relationships in green. And we also identify some marker terms that lead to a semantic attribute. And those we expand left and right within a sentence according to linguistic rules again. So that's sort of as other NLP tools would do in the context of a parse tree. We do that left and right as well. And it works quite well for negation, sentiment. And we've recently started to add a couple of other semantic things that worked well and that sort of followed our disambiguation rules and make it easy for people to quickly digest large volumes of data. And so I mentioned that we were acquired by InterSystems in 2010, but obviously Chris would never give this venue to a commercial company like InterSystems just for that. Even if he worked for INO in the past, but something really interesting happened at the beginning of this year. In February, we open sourced the INO technology, which means that the engine, so the core activity, so the Belgian IP is now available as open source, including the language models, to reach a broader audience and to broaden the set of use cases where the technology can be used. So let's take a closer look at what those use cases could be. And I'm just going to drill into two because those are the most exemplary use cases that we've been deploying our technology at. So first one is text exploration. So this is the classic bread and butter of what INO has been. When it was a separate company, when it was a standalone library, and also when we started to deploy on data platforms such as InterSystems, if you can identify the concepts in a sentence, in a text, and if you can aggregate across those concepts over a possibly large body of text, you have a much better chance at quickly navigating, for example, a patient's history, or for example, a large set of research text without overlooking something that happens to not be statistically relevant enough to drift to the top of the brute force n-grams. And it might also have just not be part of a dictionary because it was something that wasn't part of it. So text exploration deployments, we have plenty. We have some in the publishing industry and in the UK, the Veterans Administration in the US, and then here in Belgium, for example, Auxi Press, which does media clipping based in Oudregem, University Hospital of Brussels is using this for patient cohort selection. So those are all use cases where we're using the technology to be able to explore large volumes of text. So a couple of months ago, something happened in the world. COVID-19 sort of forced all meetups to go digital. What also happened in the context of this of the pandemic is that the Allen Institute for AI decided to sort of republish a very large data set full of research articles. They advertised it as 44,000 articles, but when I unpacked it all, it turned out to be a little more than that. With research articles that many of which were protected by all sorts of license agreements. And so what do you do if you get a data set of 44,000 articles? That's sort of tedious to start reading. So we deployed INO on it, and we've actually hosted this whole environment for people to just get an idea of what the technology is about. So I'll give you a very quick view of what that looks like. But this is publicly hosted, so if you're interested, you can sort of go and browse that yourself. So you can see the similar concepts, you can see related concepts, you can walk those, you can see the full. Well, this is the abstract. We also have the full data sets, and you can always jump back to the original paper if you will. So that's one example. So text exploration use cases are also the use cases where it's useful for the NLP technologies to be part of your data platform, because the challenge is not just doing the text processing, but also to make the net result easily queryable through SQL and through REST APIs, etc. So that's sort of where the InterSystems data platform was useful. Now, the second main use case, and that's really what we're pivoting towards now also with open sourcing, is feature engineering, is making sure that this technology can be leveraged to get that little bit of additional precision to improve the accuracy of your machine learning models. And for this, the data platform is suddenly a lot less important, and that's also one of the main drivers of us publishing this to open source. So I've already tried to cut down and hide all of the slides that are introducing machine learning, etc., because they're totally irrelevant for this audience, of course. But I wanted to make this small distinction between using NLP for producing input to machine learning. That's really down to feature engineering, where we're using this bag of words or bag of n-grams approaches to turn text into numeric features that can be used as input to mainstream machine learning technologies. And at the other end, there's also the more advanced machine learning to build those NLP tools in the first place. So some of the tools used on the left-hand side were built using on the right-hand side, what's on the right-hand side. But those, if you're looking at that, what the technologies that are in there, you can see a lot more advanced use cases that are getting a lot of traction these days as well. The pieces on the left, like these basic functions, these basic vectorizers that turn your text into vectors, optionally using something that was trained on a large body of text. These have also become mainstream tools that are transparently leveraged by automated machine learning platforms such as H2O and DataRobot. So this is really become something that is accessible to anybody and easy to get going with. So since we published the engine to open source, we've been really focusing on this piece. We have a corporate partnership with DataRobot, which conveniently gives us access to their platform. at no specific cost, which is helpful for us to kind of convert our team and our processes to focus on machine learning. So what we're doing with insights that we're getting from those experiments, we're trying to feed into the Python interface that we're publishing along with the INO engine. So what have we learned thus far? This has been a very humbling experience. There's really a lot of art in the state of the art these days. Also the fact that the statistics really work well. If you have a lot of data, and that happens to be usually the case when you're looking at a machine learning project, you can get really far with statistics, with purely statistics-based, with purely numerics-based approaches that don't really go at the essence of the language, which is sort of what we're very focused on. So we're starting from those techniques and try to find where we can push the needle just a little bit. Okay, what else have we found? We found that our negation detection, so where we're exploiting those expansion rules left and right, turn out to be in qualitative experiments more accurate than the equivalent that you would get out of mainstream tools such as Spacey. And then maybe that's one of the that's my question for the audience. We're looking for trouble. We're looking for problems, because many of the data sets out there that are for which you have a predicted field to train on, or for which there is a clear problem definition, they're fine with just the statistical approaches. It's only when, for example, negation starts playing a role that it gets really interesting for us. So with that, I think it's about time for questions.
Cool, thank you, Benjamin. Another quiet applause. Yay! Here we go. All right, thank you for that. It was super interesting. I had a first question for you, namely, what license did you open source it under? And for everyone else listening in, drop your questions in the that side. I don't know, in the chat, whatever side it's on. Okay.
We published it as an MIT license. Actually, our global HQ is next door to MIT, so that sounded like a good idea.
Oh, okay. Isn't that the most like permissive license? Yeah.
I don't think it's the most permissive, but it definitely is fairly permissive. Okay. Maybe also another reason why we've published it to open source is that we've over the years we've had many engagements with academic institutions that were interested in what we were doing, and sometimes those led to sort of cautious collaborations, but often they were scared by the fact that they were working with proprietary technology. For whether that's appropriate or not, it just happens to be inconvenient in some conversations, and we're now gradually picking up on some of the conversations of the past few years. So that definitely is an exciting adventure.
Cool. Okay, so we have two questions from Sophie, who I mentioned earlier is actually one of the staff members at Spacey, who you just insulted. So this should be fun. Yay! No, she's asking a really nice question because she's a really nice person. She asked if the negation detection, does it go beyond certain words or patterns? And how do you define the scope of the negation within a sentence? Okay,
maybe one word to just get the insults out of the way. We were very excited about Spacey, and we really look at it as a model to go by. So one of the things that we want to extend our Python interface with is to follow the extension mechanism that Spacey offers, because our partners at DataRobot are also starting to embed Spacey in their library. That would make this sort of a nice interlude to benefit from, or to piggyback on. So now going back to the question, how do we identify negation? So like Spacey, we will identify negation markers. So the individual tokens that represent the negation. But then as part of our linguistic processing, we will expand left and right according to some tokens that will represent or that we consider to be negation stoppers in the leftward sense and in the rightward sense. That obviously differs per language. Whereas, if I remember correctly from the experiment that my colleague Saskia did, what Spacey does is it also identifies those tokens, and then you can look at the head and other. So there's this parse tree that's available as metadata on the tokens identified by Spacey that sort of expresses a tree-like structure, and you can walk it that way, and that usually works fairly well. But it stops early in quite a few cases in the experiment that we did. But we're always happy to sit down and take a joint look and see how we can learn from one another with more vigor.
Cool. Sophie also wants you to know that she's not insulted, so that's good. And she seems to have a lot of questions about how exactly you used Spacey and how you set up the experiment. I will very gladly take that offline and set up a call together with our linguists who ran the actual experiment. I just happened to talk about it, the net results of it. But I'm glad to get in touch. All right, cool. We'll set it up. Do we have any more?
Hey, Benjamin. So working on this thing like 15 years ago or something, I remember back then we had like one MySQL database in a server in another room. That was literally that. And performance was like super important. We did C++ and like things that I've forgotten a long time ago. But I wonder now we're 2020, like what does the performance of this thing look like? How easy does it scale? Like how many megabytes of data can it process? Like do we need an hour, a day, a week to process like a 19 data set? Like how long did that take?
It differs a little bit per language. So our Japanese language model is with a certain margin slowest because it's also the biggest, it's the most complicated, which all Japanese people on this call will take as a compliment. I hope they should. But for English is the fastest one, obviously, because we put as much work into it. At a certain point, we measured that it was processing 500 kilobytes of text per core per second. And that just scales separately. So that's without ingesting the output in a database, because that obviously differs of which output you're interested in. You might be doing some processing with just part of that in memory and not be interested in all of the rest. It got a little slower since then through the addition of additional attributes, but that's still sort of what we take as a ballpark number.
Okay, cool. Thank you.
I have another question for you then. I never got what language it was written in, because you mentioned Spacey and NLTK, but I'm assuming it wasn't written in Python.
It's still C with a C++ interface, and we're now using we're now sort of projecting that through Cython as a Python interface. But most of all of our customers, all of the InterSystems customers, can only use it through the. Oh no, that's not true. But most of them use it through the interface within the database. So it's an embedded technology. It's available for data that's stored in the database or for data that you point to that is in a file system. But it's the APIs are in InterSystems space, so to say. We did also 2 years ago introduce support for UIMA. UIMA is the Unified Information Management Architecture, if I remember correctly. That's sort of a standard for NLP tools. It's not the most vibrant standard, but there's a bunch of really cool projects that live in this space. One being CTAKES, which is a whole conglomerate of NLP tools and healthcare specific knowledge to make NLP, like to apply NLP in a clinical context.
Cool. Well, it seems like we don't have any further questions from our viewers. So let me use this time to thank you once again for being here with us. I really enjoyed all of your talks. It was so much fun. And I hope to see you guys again in the comments on future meetups, or hopefully in real life at some point, so we can have an actual beer together. But for now, this is really great. So thanks again, everyone. Everyone viewing us on YouTube, let us know if you enjoyed the talks, if you'd like to change anything about the format. And thanks for sticking with us for 2 hours on a Tuesday evening. Bye-bye.
Thanks, everyone. Take care.
Thank you. Take care.
Bye.
Yeah.
Thanks.
Okay.